Let's wrap up Chapter 5 with Section 5.3, Characterization of Riemann and Lebesgue Integrability. So we've gone through and developed Lebesgue integration through these four classes of functions, as I've referred to them, starting with class 0, simple functions. These were measurable functions by their very definition. And I sort of interpreted those as kind of like giving us Riemann sums, but in the Lebesgue setting. So I'd referred to the term Lebesgue sums along the way. And it was very much Riemann-esque, except Riemann gets legitimate rectangles out because his bases are intervals. Our bases are measurable sets, but still I think of the areas of them in terms of a measure of a base times a height determined by function values. In class 1, we considered bounded measurable functions on sets of finite measure. And we didn't really explicitly make an assumption of measurability. What we showed in that section is that measurable functions are Lebesgue integrable in the sense used by that in class 1. That is, the upper Lebesgue integral and the lower Lebesgue integral, those are equal to each other. And we could have defined those for non-measurable functions as well. And what we're going to show in this section is if a function is Lebesgue integrable in the sense that its upper and lower Lebesgue integrals are equal when it's a class 1 function, then that function must be measurable. So we'll get Lebesgue integrable for class 1 functions in that sense if and only if we have measurable functions. In class 2, we considered non-negative measurable functions. In class 3, we considered integrable measurable functions. So beyond the simple functions, it's all come down to these bounded functions on sets of finite measure, these class 1 functions. The definition of the integral of a class 2 function is based on integrals of class 1 functions. The definition of the integral of a class 3 function is based on integrals of the class 2 functions. We had to avoid that infinity minus infinity stuff in that setting. So we've defined the Lebesgue integral of any measurable function, with the obvious exceptions, in terms of these ultimately beyond simple functions, in terms of these class 1 functions, bounded functions on sets of finite measure. So the purpose of this section is to show that any function which is bounded and for which the Lebesgue integral is defined is measurable. So there's the conclusion. So we're here to show that if the upper and lower Lebesgue integrals are equal, then the function must be measurable. So we get in class 1, Lebesgue integrable in that sense of upper and lower Lebesgue integrals being equal if and only if the function's measurable. Classes 2 and 3, they're all based on the class 1 stuff. So this is a general result. You might recall we did the same thing in the Riemann Bag Theorem. We dealt with bounded functions on closed and bounded intervals. Closed and bounded intervals because that's where Riemann starts, and the boundedness is part of where Riemann starts as well. Just like Lebesgue starts with some bounded stuff. Not intervals, but bounded functions on sets of finite measure. Well, technically it starts with simple functions. And then moves to the class 1 functions, very much as Riemann starts with Riemann sums and moves to this setting for Riemann integrability. And beyond that, all types of other Riemann integrals, all the improper integrals, they're defined in terms of these bounded functions, limits of these bounded things, bounded functions on sets of finite intervals that are finite in length. So improper integrals were always defined in terms of bounded things and taken limits. Pretty much what we did. Class 2 and class 3, that are defined in terms of the class 1, bounded stuff with some soups, which are effectively limits. So quite a similarity really between what Riemann does and what we do once we've got the measured theory set out. To establish that, we need the following lemma. So let's go through a proof of lemma 5.6. which states, let phi sub n and psi sub n be sequences of measurable functions each of which is integrable over E such that phi sub n is increasing while psi sub n is decreasing on set E. Let the function f on E have the property that it's sandwiched between the phi sub n's and the psi sub n's pointwise in that sense. So that's the setting. Here's the hypotheses. If the limit as n approaches infinity of the integral over E of psi sub n minus phi sub n equals 0, then we get a number of conclusions. Phi sub n approaches E pointwise almost everywhere on set E. Psi sub n approaches F pointwise almost everywhere on set E. F is integrable over E. The limit of the integrals of the phi sub n's equals the integral of F, and the limit of the integral of the psi sub n's equals the integral of F as well. Okay, so setting in terms of the sequence of measurable functions and hypotheses. All right, so first define for x and E phi star of x to be pointwise limit as n approaches infinity of phi sub n of x, and psi star of x to be pointwise limit of the psi sub n's. Now these limits exist as extended real numbers because we said these sequences are increasing. The phi sub n's increasing and the psi sub n is decreasing. So we have increasing, decreasingness of these two sequences. And let's discuss the increasing one. That means for any given x value, the psi sub n of x sequence of numbers is an increasing sequence. All right, either it's bounded and it converges to a real number, or it's unbounded and it has a limit of infinity. In either case, we're allowing these functions to be extended real valued. So in either case, the phi star function is defined. These pointwise limits all exist, allowing infinity to be their values. And similarly with the psi stars, except that's a decreasing sequence. The monotonicity of the sequences tells us, hey, every monotone sequence of extended real numbers converges to some extended real number. Converges to infinity sounds a little weird from your calculus experience, but it has specific meaning. Now, phi star and psi star, they're both measurable because they're pointwise sequences of measurable functions. The phi sub n's and the psi sub n's are measurable functions, and these things by definition are the pointwise limits of those. Proposition 3.9 says a pointwise limit of a sequence of measurable functions is measurable. The limit functions are measurable. Okay, so we've got measurability. We need to tie these limits in with the function value. And so we can replace this statement, phi sub n approaches F pointwise almost everywhere, with the statement phi star equals F almost everywhere on E, and similarly for the psi star. And since we've defined those as the limits. Okay, now we've got phi sub n less than or equal to F less than or equal to psi sub n. That's where those functions came from. So the limit values will satisfy inequalities of a similar sort. The phi sub n's were monotone increasing, so the limits will be greater than or equal to. Also, f acts as an upper bound, if you like pointwise, for all of these phi sub n's. So f acts as an upper bound on the limit phi star. And similarly with the psi's, except now we've got a lower bound of f, and the psi sub n's was a decreasing sequence. So the monotonicity of the sequences, along with the behavior in terms of bounds of limits, gives us this inequality for these 5 functions. So we can, from this, we can extract that 0 is less than or equal to psi star minus phi star, just taking the phi star and subtracting it. Further manipulation giving us phi sub n minus psi sub n is greater than or equal to this quantity here. We could go into the algebra in more depth. It's just arithmetic manipulations. So we get these inequalities, and this holds for all n. We've got monotonicity of the integrals. We got monotonicity, the integrals 3 or 4 times over. Here, we're dealing with non-negative functions. So each of these, phi sub n minus psi sub n, is non-negative, as is their limits, psi star minus phi star. So we're dealing with non-negative functions. We have a monotonicity of integrals for non-negative functions. I guess it was theorem 4.10. So this is our, what was this, class 3 of functions. And the inequality here implies a corresponding inequality on the integrals, monotonicity of the integral. This also holding for all n. Now, we had hypothesized, so here's that hypothesis, that the limit as n approaches infinity of the integral of psi sub n minus phi sub n. We hypothesized the limit of that sequence of integrals was 0. So let n approach infinity. We get this upper bound approaching infinity, upper bound approaching 0 as n approaches infinity. We've got this bounded below by 0. We can make this arbitrarily small. In fact, it has a limit of 0. So it must be that this is 0. Now, this is an integral of phi star minus psi star, an integral of a non-negative function producing 0. Well, proposition 4.9 says if an integral equals 0 for a non-negative function, then that function 0 almost everywhere. So psi star minus phi star is 0 almost everywhere. Or in other words, psi star equals phi star almost everywhere on set E. Now we've got the sandwiching as given here, right? It came out of the inequality above. We got F sandwiched between phi star and psi star. And the phis and the psi stars are equal almost everywhere. All right. Also, they're the limits of the phi sub n sequence and the psi sub n sequence, respectively. Oh, let's see. I got an almost everywhere floating around in here also. So we must have that the limits are equal to function f almost everywhere on set E as well. So that was one of the claims. We've got the phi sub n's approaching f, and we've got the psi sub n's approaching f. In other words, phi star equals f, and psi star equals f almost everywhere on set E. So there's the convergence part. F, we didn't put much on the way of hypotheses on f other than it being sandwiched between these other things. So we can conclude that f is measurable. It's an almost everywhere point-wise limit of a sequence of measurable functions. The phi star and the psi star, those were measurable. And f equals those almost everywhere. So f itself is a measurable function. Okay. We still need to deal with, here comes integrability of f and the value of the integral. Next, let's go back up here one more time to this inequality and consider, say, n equals 1. So we'd have phi sub 1 is less than or equal to f is less than or equal to psi sub 1. This holds for all n, take n equals to 1. And we'll get this statement upon rearranging. So subtract the phi 1s from, subtract the phi 1s throughout, and that'll produce this inequality. So again, we've got some non-negative functions. Let's see, phi 1 and psi 1 are integrable. All of those phis and psis were integrable. That is, their integrals are finite. So we've got this function bounded above by an integrable function. The integral comparison test will tell us then that this is an integrable function. So we've got f minus psi sub 1 is an integrable function. But psi sub 1 itself is an integrable function. So from that, we get that f itself is an integrable function over set E. So no infinities in any of this. All right, so f is integrable. That was one of the conclusions. Here's the statement again. So how are we doing? We've got the almost everywhere pointwise convergence claimed here and here. We've got f is integrable. The last thing to show is the value of the integral equals the limit of the integrals of the phi sub n's and the psi sub n's. Okay, from those inequalities we previously had, we had 0 is less than or equal to the integral over e psi sub n minus the integral over e of f in using linearity. In what we had above, the integral of the difference is a difference of the integrals, so we get an equality here. Linearity as applied to what class of functions do we have? Integrable functions. So linearity applied to integrable functions. And let's see, we can say this is less than or equal to the integral over e of psi sub n minus phi sub n. Remember, the psi sub n is an increasing sequence. Psi sub n is an increasing sequence. Okay, so it increases up to the function values of f. So here we're subtracting something lesser away. So the phi sub n minus, or psi sub n minus phi sub n function is greater than or equal to psi sub n minus the f function. These are smaller, we're subtracting less stuff. And so monotonicity will give us this little inequality here. We had hypothesized the limit of such an integral equals 0. So for n approaching infinity, this approaches 0. We've got this bounded below by 0. So this must actually equal 0 after taking the limit. That is, the limit as n approaches infinity of the integral of the psi sub n's must equal the integral of the f. Similarly, taking this inequality we get from the previous slide, linearity, using the fact that the psi sub n is decreasing versus the phi sub n being increasing, draw a similar type inequality and a similar type argument. Okay, we've produced this. I know as n approaches infinity, this approaches 0. So as n approaches infinity, these two things must have the same limits. That is, the integral over e of the phi sub n's must have a limit of the integral over e of f. So this is a lemma in the direction of showing integrability implies measurability. So the following result deals with necessary and sufficient conditions for Lebesgue integrability, not the integrability in the sense of finiteness that we used it in section 4.3, but integrability in terms of upper Lebesgue integrals and lower Lebesgue integrals being equal in the setting of class 1 functions, bounded functions on sets of finite measure. And theorem 5.7 says exactly that. Let's just look at it in the Beamer file. It says, let f be a bounded function on a set of finite measure. Notice there is no assumptions of measurability. That's what we're going to prove. F is Lebesgue integrable over E if and only if f is measurable. Okay, well, if f is measurable, we had the integrability. Theorem 4.4 showed us that it worked, is how I worded it. Our definition of Lebesgue integral worked for any measurable function. So we need to look at the converse by supposing we have a Lebesgue integrable function that is at the upper and lower Lebesgue integrals are equal. Those were defined in terms of simple functions as given here. So even if f isn't measurable, then we can still find these simple functions less than or equal to f, and we can still do this soup stuff. Our claim is we only get equality when we're dealing with a measurable function. Okay, so here's what we had for upper and lower Lebesgue integrals. By definitions of soups and nths, since this thing is a soup over the set of numbers produced based on simple functions which are integrated and satisfy a certain inequality, then we can find ourselves a sequence of simple functions, phi sub n less than or equal to f, that converges when we integrate to this value. There's a sequence of functions, phi sub n less than or equal to f, such that when we integrate the phi sub n's, they have a limit equal to this value, the soup. And by properties of infima, we can do the same thing with the size. There's a sequence of simple functions psi that when we integrate and take a limit, we get that value. I'm not saying you can get that value. I'm saying you can get that value as a limit. As I've always said, soups and ants are really just limits. Here it's written out explicitly. Well, we were just talking about a limit of such functions, but it isn't guaranteed that this phi sub n's and psi sub n's, these two sequences of functions, are increasing and decreasing as needed, but we can fix that. All right, so now if we take the difference of the upper Lebesgue integral and the lower Lebesgue integral, and we've assumed that's 0, we're assuming integrability, Lebesgue integrability. We've written both of these as limits, as given. Here we've got a difference of limits as n approaches infinity. Property of limits. Limit of the difference is the difference of the limits. So we can write that as a limit of this difference here. Now we can use linearity on the appropriate kind of functions. So these phi sub n's and psi sub n's, these were simple functions, right? So it's the linearity property corresponding to simple functions. They came out of the definition, remember, of upper and lower Lebesgue integrals. Now we can take here's where we're taking care of the monotonicity ideas. The max and min of a pair of simple functions is again simple. So we can actually say the maximum of over I ranging from 1 to n of phi sub I and the minimum I equals 1 to n of the psi sub i's. These are also simple functions. These are also measurable. We'd addressed that at some point in the past about maxes and mins of collections of functions. But we're definitely getting measurable as well. So we can replace phi sub n with this maximum deal, the maximum over the first n phis pointwise, and we could replace psi sub n with the minimum over the first n psi sub i's pointwise. And by doing the max and min thing, then we get the increasingness that we need on the phis and the decreasingness that we need on the psi's. By doing the min thing, for example, of course, as n gets larger, we're taking minima over a larger collection of things, and we'll produce something that's decreasing. So without loss of generality, we can assume that these sequences are increasing and decreasing as needed. So now we can apply that lemma that we just dealt with to these. By lemma 5.6, we can conclude that the phi sub n's converge to f pointwise almost everywhere on E, and similarly for the psi sub n's. All of these phi sub n's are measurable, and we've written f as a pointwise, almost everywhere, pointwise limit of these measurable functions. But wait, the pointwise limit of a sequence of measurable functions is measurable, proposition 3.9. So the function f must be measurable, and that was a conclusion that we wanted. Okay, so Lebesgue integrable if and only if measurable. All right, a little more conversation. We're done proving things. The book goes to prove theorem 5.8, which they call simply Lebesgue. This is what we call the Riemann Bag Theorem. That is that a function f bounded on a closed and bounded interval AB is Riemann integrable if and only if the set of discontinuities has measure 0. So we actually use that as motivation as to why to look at Lebesgue integration. So we'll leave our proof from the supplements earlier instead of redoing that. It's, I think, a reasonable question to ask. Did Riemann know this stuff? Did Riemann know what we've called the Riemann Bag Theorem? What our textbook, Royden and Fitzpatrick, simply calls Lebesgue. Riemann did know this stuff. Riemann knew this result himself. He would not state it, of course, in terms of measure theory. That's the invention of Lebesgue. We're going to quote a reference. I think it's from 1854 from Riemann, or related to some Riemann work from 1854. And measure theory it's in the ether around the year 1900, but it's not settled until Lebesgue settles it in 1906 with his dissertation. I think it's 1906. So it's about 50 years before measure theory is a thing. Yet Riemann still goes through and states what we would call the Riemann-Lebesgue theorem. He doesn't state it in measured terminology. He states it another way. Riemann, he knew the Riemann-Lebesgue theorem. Yeah, I wouldn't say things in terms of measure. Here's a quote from A History of Analysis, an edited volume of various collection of papers on history of analysis from 2003. It's an AMS book, quoting from that. The total length of the intervals in which the oscillations are greater than sigma can thus, whatever sigma may be made arbitrarily small by an appropriate choice of D. The statement is also sufficient. Riemann established this too. In an annotation, Dedekind, as editor of Riemann's works, referred to a handwritten note of Riemann's in terms where he completed the proof, the if and only if. Now this oscillations deal, that's how we dealt with discontinuities when we proved the Riemann-Lebesgue theorem earlier. Now this idea, something or other can be made arbitrarily small by an appropriate choice of D. This is pretty out of context, but what they're doing there is they're isolating the points of discontinuity on, how about this, a set of measure less than D. So that's the arbitrarily small part. So there's sort of it's playing sort of a role of an epsilon here in terms of how they're covering the set of oscillations, the total length of the intervals. I guess I'm just going to highlight that part as well. So they're covering the places where the oscillation is big with these intervals. And the lengths of the intervals is being made as small as you would like, except for 0. That's measure theory. Use open intervals, that's outer measure. So this it's exactly what we went through in our proof, it turns out. The reference here, it's 1854, just for the record. There's the paper that's being quoted. This mention of oscillations, right? That's how we approach the Riemann-Lebesgue theorem, and the Riemann-Lebesgue handouts near the beginning of the course. The idea that the total length of the intervals can be made arbitrarily small. That's dealing with the measure 0 stuff. And well, the last little comment, as you know, hey, we got away in that Riemann-Lebesgue theorem handout. We got away with talking about measure 0 without all the woes of a positive measure sets and theory of measure. And so did Riemann. So non-measurable sets are not an issue if we restrict our attention to measure 0 sets. Yeah, we can't do integration if we restrict ourselves to measure 0 sets, but we can wrap up this Riemann-Lebesgue theorem stuff by only addressing measure 0 sets. To get to a statement of this in terms of measure theory really does require Lebesgue, but as I mentioned, the ideas were out there in the mathematical community. The story of the Riemann-Lebesgue theorem carries on for several more decades until Lebesgue settles it. Quoting from Morris Klein's Mathematical Thought from Ancient to Modern Times, dated book, still in print. It's still in print in paperback, but it is, actually it's a fairly thorough, it's a very thorough history of math. It's technical, so it goes into the technicalities. Take a history of math class at the junior level, and it doesn't get into the very deep math stuff. This 3-volume set here, this gets into the deep math stuff, even though it's about 50 years old at this stage. A quote from that reference, Darboux, we've run into Darboux. Darboux then shows that a bounded function will be integrable on interval AB if and only if the discontinuities in f of x constitute a set of measure 0. This is done in 1875. Darbo's not saying it like that, but he's independently found this result as well. By the latter, he meant that the points of discontinuity can be enclosed in a finite set of intervals whose total length is arbitrarily small. This formulation of the integrability condition was given by a number of other men in the year 1875. Yeah, well, it's part of the price of reading a 50-year-old book. They're sort of very 70s wording in relation to the gender stuff. Lebesgue himself seems to have presented a proof, and hey, he's the measure theory person on this. Lebesgue showed, here's a reference from 1904, that a bounded function is Riemann integrable if and only if the points of discontinuity form a set of measure zero, also quoting from that 1972 reference. So these ideas were around. Riemann sets up the idea of Riemann integration, and he put necessary and sufficient conditions on it. Riemann knew when it worked and when it failed. But that's most cleanly explained in the setting of Lebesgue measure. So really, the Riemann-Lebesgue theorem belongs in the realm of a graduate level analysis 1 class. I've been lucky to find a reference that allows us to approach that and actually do it in a senior level analysis class, because we'd address measure zero without addressing measure in all its glory, and really the concerns over non-measurable sets. And that's pretty much real analysis 1. The next chapter includes some additional properties of integrals, interactions of Lebesgue integration and differentiation, but these chapters covered up through this point. That's pretty thorough introduction to real analysis 1, Lebesgue measure, and Lebesgue integration. So thank you for listening. Have a nice day. Bye-bye.